I started recording. Okay, so good morning once again. So today, even though you are going to sit the test today, but it's not interfering with your with your preparation, because you know what, you will need to do matrix exponential, or at least matrix functions, during your test today. And we are going to go through one of these examples. It will be used in our new topic. And besides, do you remember you needed to find eigenvectors for 3 by 3 matrix, which was quite a hassle. And again, we are going to explore such problem today. So maybe this tutorial will be helpful to you to do a sort of revision of the previous material. Okay, so it's time to begin. So the first topic today will be differential equations, or systems of differential equations. Systems of differential equations. It turns out that this technique of matrix exponential can be used quite effectively solving these systems. But first of all, let's have a look at how they look like, these systems of differential equations. There are a multitude of types, these differential equations, but we are going to deal with only one of these types. So they call differential because they contain derivatives of functions. So x and y are functions now. I want to bring your attention to the fact that they are not variables anymore. They are variables, but these variables are not numbers, they are functions. So they are both functions of time. T is time. So, and this is the left-hand side of these equations, and the right-hand sides will look like this: a1x plus b1y, a2x plus b2y. So these a and b's are just numerical coefficients. But your task will be to find these two functions, x of t and y of t, which would satisfy this equation. So if you calculate the derivative of x and y and substitute it in the left-hand side, it should bring you the correct equality. Besides, they often give you so-called initial conditions for these functions. Initial conditions. So what are these guys? X of 0, when t is equal to 0, could be some number. Let's denote it C. And y of 0 could be some number as well. So these C and D's are real numbers. Okay, so what next? How do we solve these equations, these systems of equations? The thing is that matrix exponential can be used very effectively, very beautifully, and it's no problem to memorize this algorithm. It's very short, this algorithm. So, and I forgot to mention that there are actually at least two methods of solving this system. And they are both mentioned in your lectures. So if you're really interested in going deep into things, you're welcome to watch the lectures once again if you haven't done already. But now, due to limited time, I need to give you only one method, which is the best actually. So what is this method? This is matrix exponential method. Matrix exponential method or technique. Matrix exponential, let's call it technique. Matrix exponential technique. So it consists of 3 steps only. Oh, it looks like blue is much better. It's fresher. Okay, so the first step is to write down so-called matrix of the coefficients for this system. You look at the right-hand side of this equation, and you explicitly see that the terms with x's are positioned in the first place, like the first terms, and they have coefficients a1, a2. So this will form the first column of your matrix. And similarly, y's, coefficients in front of y's form your second column. Just a piece of cake, nothing fancy. Then the next step will be to find lambdas. Find lambda 1, lambda 2, which are eigenvalues of this matrix, because in the next step we are going to use Cayley-Hamilton theorem. So that is why we always need those lambdas. So what is this Cayley-Hamilton theorem? It allows us to find matrix exponential. So e to the power of at as you know from the previous tutorial, is alpha 1 times matrix itself plus alpha 0 identity matrix. So you know how to do it. I'm not going into details explaining this third step, because you're well aware of how to do it. We will go through this detail when I start dealing with a concrete example. And finally, the fourth and the last step is to find the answer. So to find the answer, there is a very nice formula. So the column of unknowns, which are functions, of course, but I'm deliberately omitting these parentheses, x of t, y of t, because it will make my notations too messy. Okay, so it's matrix exponential, which you calculated in the previous step, times x of 0 and y of 0, which are initial conditions. So that's where you use these initial conditions, which were given to you from the very beginning. So you just substitute this column CD, maybe we'll put this CD. But then, so that's it. As you can see, the algorithm is pretty straightforward. Nothing fancy. It just needs some, accuracy, following step by step. But I need to make a very important note, because what if you are not given these initial conditions? What should you do in this case? So let's make a note, very important note. That is why I'm writing it in red. If there are no initial conditions, what do you need to do? You just need to pretend if they are there. So you need to substitute x of z c, and y of 0 you should substitute c and d here. And as a result, you will get your answer, your functions x of f, in terms of c and d. But it's you need to get used to it, of course. Some people get really put off by this necessity to deal with not numbers but with expressions. But I don't think it's a big issue for you, because you're not high school students anymore, you're university students. And that is why, this is the reason why I chose from question 2a from your tutorial sheet, because it does contain this more difficult case. So question 2a, it looks just like I just mentioned. It doesn't contain initial conditions. That is why I found it more interesting, more difficult. I decided to go over this example. So I'm writing this question from there. So this is the system of equation which is given to you, and no initial conditions at all. It means that we need to sort of invent them by ourselves. Let's write them down here. So x of 0 will be c for us, y of 0 will be d for us, and that's it. That's what we are going to substitute in during our last step, and it means that we will need to simplify our answer quite significantly. It will be a little bit time consuming compared to the case when c and d are just numbers. But numbers are not interesting, it's too simple. That is why I chose this example. Okay, so let's start applying our algorithm. So the very first step, there's my blue looks much better. So the first step is to write down the metrics of our system. Sliding down. There's nothing easier than this. So x's on the right hand side have coefficients 3 and 4. This is our first column. And y's have coefficients 4 and minus 3. That's it. This is our very first step. The second step was to find lambdas, that is eigenvalues of this matrix. You've done it million of times, so nothing fancy about it. So we need to solve these equations. Okay, 3 minus lambda times minus 3 minus lambda minus 16 is equal to 0. And you know what? I'm going to save our time a little bit. It's a very easy task. It's just a quadratic equation, but it's I may spend like maybe 15-20 seconds on it. I prefer to save everyone's time. So I'm just rewriting answers. But I lost my answers. No, I can't save time. Because I can't find the page where I prepared these answers. Okay, I have to do it. Lambda squared minus 6 lambda, what else? Minus 9 minus 25. I hope it's correct. Okay, lambda squared, let me plus 3 lambda minus lambda. It looks like I made a mistake. Ah, my goodness. It's funny really, because I wanted to save time, but as a result, I'm not saving it. I do it in this way, okay, much quicker. So it will be lambda squared minus 25. Ah, no, it was correct. Lambda 1 is equal to 5, lambda 2 is equal to minus 5. Okay. So there's nothing terrible about it. Okay, we did get our lambdas, nothing new about it. And now comes the third step, finding matrix exponential. Again, there's nothing new for you, but I think that this particular step is especially useful for you in terms of today's test, because the test does involve matrix functions, maybe exponentials, and so on. So it's an important step. Okay, so what do we need to do? Before calculating matrix exponential, we need to use this equation. E to the power of lambda t is equal to alpha 1 times lambda and plus alpha 0. We use this equation to find our coefficients alpha 0 and alpha 1. Of course, you remember that it was this the equation associated with this matrix exponent here. Okay, so to find these alphas, we need to dig up two equations from somewhere. But we know that we already have two lambdas. We can substitute them into this red equation, and that will be it. So instead of lambda, I'm substituted 5 here. E to the power of 5t is equal to alpha 1 times 5 plus alpha 0. Then it will be e to the power of minus 5t is equal to alpha 1 times minus 5. You know, guys, I'm very absent-minded this morning. It's not question. I wanted to give you question 2b, but instead I gave you question 2a. Okay, it does have initial conditions. Sorry for being so absent-minded. So it was 5, it was 1. But again, I can pretend that I didn't have these initial conditions, and I can do both tasks. Maybe it's even for the better that I was so absent-minded. No problem. Let's get back to this system. Now we need to solve this system for alpha and alpha 1, alpha 0. But you noticed before, of course, that I never used Gaussian elimination method for solving such small and simple systems. It's better to use some tricks which you found out, which you learned in high school. So, for example, it's allowed to add equations within a system, and it also allowed to subtract them from each other. And it looks like our system is so wonderful, so beautiful, that we can use both of these operations. Look at this. If you add these two equations together, let's do it. So the left-hand side will give you e to the power of 5. So I added together the left-hand sides. And if I add up the right-hand sides, these two terms will disappear, will cancel out. And we will have only these two alpha 0. And we immediately get alpha 0. Very beautiful technique. Plus e to the power of and divided by 2. So we already have our first alpha. Very nice. And again, if you look at these equations again, you might realize that it might be a good idea to subtract them from each other. If you subtract the second one from the first one, look at this. E to the 5t minus e to the minus 5t. These were left-hand sides. On the contrary, these two guys will cancel out, but these guys will give us 5 minus minus 5 will be 10 alpha 1. And again, you can express alpha 1 here. Look at this. Very beautiful solution. Very nice and effective. So we already get our alpha 1 and alpha 0. And now the second step within this third step is to find matrix exponential at last. I need to turn the page. Okay, but I'm trying to keep everything on the screen for you. Okay, so the next step is to remember that we are dealing with this equation. E to the power of at is alpha 1 times a plus alpha 0 times identity matrix. And now we need to substitute our information. Which is our information? These are these guys, alpha 0 and alpha 1, which we just calculated. But you know, it's better to linger, to postpone it, because it's better to substitute our matrices first, and only after that we can substitute alphas. Otherwise, it will be such a big mess there. I'm afraid that I will start making careless mistakes. So matrix A, 3, 4, 4 minus 3. instead of A here, plus alpha 0 gets rewritten, copied, and identity matrix here. Now we can make this, we can simplify this expression. We can do this matrix operation. This is very easy. We've done it in the past. So 3 alpha 1 here plus alpha 0 here. The next element will be just 4 alpha 1. The next element, this element, 4 alpha 1 plus nothing, minus 3 alpha 1 plus alpha 0. So we are almost there. We are almost there. But now we need to substitute our alphas. Oh, it's quite annoying, but what can you do? Okay, I'm going to write it. I'm trying to look at the time all the time. Okay, 3 times, I need to keep them in the field of view, which is not quite easy. So these are my guys, alpha 1, alpha 0. I don't have enough space, maybe. So, no, now I need to keep this guy as well. Okay. I think that you believe me. So I'm copying alpha 1 here, e to the power of 5t minus e to the power of minus 5t. I'm running out of space at the same time. Plus 1 over 2. And these pluses. Running out of space. Look at this. This element on the top left corner, took up all the space here within the matrix. Oh, so bad, so bad. Maybe I just put these vertical bars not to get things too messed up, and just write 4 alpha 1 here for a while. And so 4 alpha 1 is here. 4 alpha 1 will be 4 over 10 e to the power ft minus e to the. It's quite annoying part, it's nothing easier than to do these simplifications, but at the same time it's very time consuming and a little bit annoying. But what can you do? You know what, I have an idea. I wanted to save some time, and that's where I'm going to do it. Of course you are quite capable of doing these simplifications. I have no doubt about it. You are university students, as I said before. That is why let me give you just answers. Okay, so e to the power of t, after all the simplifications, it's better to pull out 1 over 5th. You will see it. If you don't believe me, you can check my transformations later. Okay, so that will give us 4 to e to the power of 5t plus e to the power of minus 5t. This element to the right will be 2 times e to the power of 5t minus 2 e to the power of minus 5t. And the second row will be 2 to the power of 5t minus 2, no, the same as here. And this element is just like this one. So 4. No, it's not quite like this. No, I'm mistaken. Yeah, they're different, of course. But I already have an answer here. So this is the e to the power of 5t. Okay. So I saved a little bit of your time. Okay, and now comes the last part. The last part is to find finally the answer to our differential equations. We are given nice formula. That is why let's start doing this. So the answer will have this form: e to the power of at exponential, which we just calculated, and here comes the column of initial conditions. Okay, let's do the easier task first. The easier task first, because in this particular task, question 2a, it was here, question 2a, you are given these initial conditions, which are 5 and 1. Okay, so we need to rewrite this matrix, which is matrix exponential, and multiplied by this column. Very annoying, because you need to do so much writing. 5t plus e to the power of minus 5t. Nothing. There's nothing bad about it. It's very easy. This is quite consoling that it's all very easy. You just need to be very careful and concentrated. Okay, so it was e to the power of at. This is matrix here. And we need to multiply it by column 5, 1. Again, 5, 1. So it's very simple again. It's just matrix multiplication. So 1 over 5th, let it be in front. And then what we need to do? We need to multiply this first row by this column. Too much writing again. Okay, but I'm going to do it. 5 times this guy. 4. I'm just rewriting it silently. Plus this guy times this. So it will be just 2 minus 30. And after that, as you may guess, we need to do some simplifications. Okay, but we are not finished yet. We need to do the same for the second row. So this first element gets multiplied by 5. 5 times, I'm rewriting it. And plus this guy, because it's multiplied by 1 only. And now the final answer will be if you do some simplifications. If you do this multiplication and find the like terms, I'm not going to write this. I think it's too easy for you. So it will be 20 times e to the power of t. And here you have 2. Maybe it's better to highlight these like terms. This and these are like terms. It will give us 22. 22 e to the power of 5t. And similarly, these and these are like terms, other like terms, but this one has coefficient 5 in front. 5 minus 2 will be 3. So it will be plus 3 e to the power of minus 5t. And the same, you can do the same the second row. I'm just rewriting the answer for you because you already know everything. So this is our final answer to this problem. Question 2. Question 2.1 or question 2a, as you can see. As you can see, things are pretty easy, but you need to be very careful, very precise, very concentrated to do all these simplifications properly in the correct way. So that's it. But I promised to tell you how to deal with this task if you don't have these initial conditions. Let's do it. Let's spend like 10 minutes on it. It's really worth it. So like 4a, let it be 4a. What if you don't have initial conditions? In this case, you need to put up with the fact that your x of 0 is just c, y of 0 is d, and your column will be just c and d. You can't substitute anything without instead of c and d. Let's do this simplification because it's really a little bit difficult. Okay, so the formula is the same. Again, of course, e to the power of at. At times, I'm writing cd from the very beginning. Now I need to rewrite this e to the power of et for the second time. So how does it look like? 4e to the power of 5t plus e to the power of 5 minus 5t. This guy was 2. Maybe I better put vertical bars because my writing gets a little bit messy. T. This was 2e to the power of 5t. I hope I'm not sliding out of the field of view for you. And this was so I copied this matrix exponent e to the power of et, and now I need to multiply it by cd. So these simplifications, this transformation become even messier, But what can you do? You do need to know how to deal with it. Okay. So the first step will be just to do this multiplication. So remember, just before, in the previous task, we have 5 and 1 here, but now we have c and d's. It will look like this. C times this first guy. Plus d times this second guy in this row. D times 2. And I'm just copying these guys. So as you can see so far, nothing bad is happening. Just you need to be very, very careful. Okay, we are doing the same with the second row. Second row gets multiplied by this column again. So these elements, I'm just rewriting, copying them all the time, plus d times this guy. So there's nothing interesting for you. Maybe you're just getting puzzled why I decided to show you this example. But wait a bit. Now, of course, we need to simplify to find like terms. Let's find them. So this is the term containing e to the power of 5t, and here it is again. But this time coefficients in front of them are pretty unusual. They are not numbers, they are like 4c plus 2d. But we have to put out with it. So 4c plus 2d times e to the power of 5t. And I'm going to highlight it in the same manner so that you don't get lost. Okay, so pretty simple so far. And the next type of terms is this one. Let's call them blue terms. light blue terms. So they have coefficients c in front of this and minus 2d. So c minus 2d times e to the power of minus 2t. So this is going to be blue term. Okay, so we managed to calculate the first row. Now we need to do the same the second row. I need to find more colors. Green. This one and this one are green terms, and they will give us what sort of coefficient? 2c plus d and times e to the power of 5t. So this was green term. Okay, and finally, what else I need? I need orange here. Orange. So these guys are orange terms. And they will give us coefficient minus 2c plus 4d times e to the power of minus 5t or minus 5. I made a typo here. So this was orange term. Okay, we are almost done. By almost, theoretically, you can leave the answer in this form, but you know what? It looks too ugly. It doesn't look beautiful. It looks so messy and awful. Mathematicians always try to simplify, all the expressions just to give them, more elegant look. This one doesn't look like that. Just let's have a closer look at these coefficients. So we have e to the power of 5t here and here. And coefficients look like expressions, but you know what? They are proportional. Can you see? This, if you take this coefficient and multiply it by 2, you will get this coefficient. So there is a relationship between them. And you know what? We can denote this. I'm running out of ink, unfortunately. No colors anymore. Okay, magenta works a little bit. So if you denote this coefficient C2, C1, this one will be 2C1. Very nice idea. But my marker is letting me down. So what? So as a result, we get 2C1 times e to the power of 5t here plus something. And C1 e to the power of 5t. Look at this. Looks much more elegant, much more concise. And so maybe inspired with this thought, we move to the second term and look at their coefficients. Look at this. Again, the same thing. Here you have this expression, but if you multiply it by minus 2 this time, you will get this impression. So again, we can make a beautiful notation. So let this coefficient will be C2, and this one will be minus 2C2 in this case. Very beautiful. I think it's very beautiful. So plus C2 e to the power of minus 5t and minus 2C2 e to the power of 5t. And that's how these answers look in your answers. But not in this particular task, because we can even write down separately x and y, but I don't think it makes sense to spend our time on this. Of course, x is equal to this expression times 1 over 5, and y is equal to this expression times 1 over 5. But I think it goes without saying. You can easily figure out it without myself. So I'm really happy that I managed to show you this technique, because question 2C does contain this case without initial conditions. So I highly recommend you to try and solve this question 2C by yourself, because you will have to use the same technique about this notation C, D, and so on. So, okay, so we are finished with this topic. As you can see, there's nothing fancy about this topic. You just need to know this very short and straightforward algorithm. Okay, and now it's time to move to the second topic, which is quadratic surfaces. Quadratic surfaces. I have to clean up my table a little bit. Let's write down this topic, the name of this topic, the title. Okay, so 2 quadratic surfaces. Quadratic surfaces. You know, this topic is pretty similar to the previous one, which was quadratic curves. The news is that we will have more arithmetic to deal with, because the canonical equations of surfaces look pretty much like canonical curves of curves. Canonical equations of curves. Sorry, I didn't have enough coffee this morning. And so, and we will be faced with the same task. We will be given the general form of some surface, and our task will be to bring it to canonical form using the same technique, the same algorithm, absolutely the same. But the bad news is that this was a good news. But the bad news is that this time we will have to deal with matrix 3 by 3 rather than 2 by 2, and of course it involves more work, and it's more time consuming. And but I think that on the other hand, it's very good that I will show you this example today just before your test, because you will have the opportunity to refresh your knowledge as to how to find eigenvectors and eigenvalues for matrix 3 by 3. So it's always done for the better. Okay, but now we need to start. So as I said before, quadratic surfaces have canonical forms, canonical equations, first of all. So where's my blue? So canonical equation. Let's write down canonical equation first. Canonical equation looks like this. So A times x1 squared plus b x2 squared and plus c x3 squared is equal to 1. So this is canonical equation of a surface. As you can see, the only difference with the canonical equation of the curve is that it has additional third term, x3. By the way, I switched from old notations. No, we use the same notations. Yeah. So we used the same notations when we were dealing with curves, x1 and x2. So the only difference lies in this term. It immediately brings us to the 3D space. 3D space. We have three coordinates here, x1, x2, x3. Okay, so if you do have this canonical curve, how to determine which, not curve, surface, sorry. How to determine which kind of surface is hiding behind this curve? It all depends, the answer is that it all depends on the signs of these coefficients, A, B, C. They can be positive, can be negative, some of them can be even 0. And as a result, you have 5 canonical surfaces. Let's write them down. So the first curve, if you have all pluses, so all these coefficients A, B, C are all positive. If they are all positive, you are dealing with ellipsoid. Ellipsoid. Unfortunately, I don't have time to plot them, even though I really like this, plotting. But unfortunately, I don't have time. So, please turn to your lectures or study guide to look at these beautiful surfaces. They do look very beautiful. Okay, so my task is just to refresh your knowledge about the types of these surfaces and how to recognize them. Okay, so this was the first case. All these coefficients I, B, C are positive. The second case will be if there is one negative among them. This will be one sheet hyperboloid. Very beautiful curve, but as I said before, I'm not going to plot them. I'm only going to list them. The next case, plus, minus, minus. In this case, you are dealing with two-sheet hyperboloid. Two-sheet hyperboloid. It looks pretty different to the previous one, even though they are both hyperboloids. Okay, the fourth case, plus, 0. One of the coefficients could be even 0. And this case is pretty confusing for some people, because 0 means that you are missing one term. For example, let's imagine that we don't have this term here at all. And you might get under the impression that you are dealing with a curve rather than the surface, because you do have only two variables. But in this case, read the assignment to your task very carefully. If they claim that you are dealing with the surface, it means that you are dealing with this case, not the curve. Okay, so it means that it will be ellipsoid, cylinder. What did I say? Cylinder. Elliptic cylinder. And the last case, the fifth one, is plus, minus, 0. In this case, you are dealing with a hyperbolic cylinder. Very beautiful surfaces. It's a pity I can't plot them. So this is our list. And you know, but I suspect that they usually won't ask you to plot these surfaces during tests exams, because it's the first reason it's very time consuming. The second one, that you need to be a really good artist, you know, to make this plot look very beautiful. Because and for most of the people, it's quite a problem, you know, to draw a very beautiful picture. That is why they only ask you to determine the type of the curve. And as you can see, it's very easy. You can just you need to just to look at this signs, plus or minus. Okay, so it was canonical curve. What about general form, general equation, general? So general equation, of course, it contains more terms. Let's have a look at it. The first two terms can be copied from our canonical curve. Let's do it. A x1 squared plus b x2 squared plus c x3 squared. These were the terms which I copied from a canonical term. But then we have, unfortunately, we have two more terms. Look at this. 2d x1 x2. We are pretty familiar with this term. We did have it in general form of curve, quadratic curve. But this time, unfortunately, we have two more terms because we have more variables here. So 2f x1 x3, and finally 2e x1 x2 x3. Unfortunately, I messed up alphabetical order, but it doesn't matter. It doesn't matter at all. You need to get the idea, not the not the concise notations and everything. Okay, so this is general form. Why does it look so ugly? Not ugly, but such a big expression. Why do we have these annoying three terms? You know, the reason is that your ellipsoid or whatever, your canonical surface can be rotated around origin. And if you rotate this beautiful surface, its equation, you know, has this additional terms. And your task, as you may have already guessed already, will be to bring this general equation to canonical form, which means that you will need to find this new system of coordinates, which is y1, y2, y3, in which this equation would look beautifully, would look canonically. So as a result, as you can see, you are faced with the same task, and you know what? The algorithm is the same. But as I said before, it involves matrices 3 by 3. That is why it will look longer. This algorithm, it will involve more calculations, and they will all be a little bit more time-consuming. That's it. So but you know, first of all, you need to know how to write down this matrix of the left-hand side. Let's discuss it because it's quite an interesting thing. So it will be matrix A, but this time it will be 3 by 3 matrix. That is why let's draw some dots here. They will serve as a placeholders for us. So we need to fill up this matrix, this 3 by 3 matrix. You know, the best approach is to use this trick. So you might think that every column in this matrix will be associated with variable x1, x2, x3. And the same applies for every row. Let's imagine that every row is associated with variable. So rows and columns are associated with our variables given in this order: x1, x2, x3, xn, xn, xn. And then if you need to determine the coefficient in the top left corner, you should look at these associated variables. So x1 times x1, you need to multiply this, it will be x1 squared. It means that you will need to find the term with x1 squared and look at this coefficient a in front of this. So it's a. Okay, let's move along the diagonal first. So this element corresponds to x2 times x2, which is x2 squared. Where's this term? This is term, and it has coefficient b in front. That is why we put b here. And similarly, this location corresponds to x3, which is x3 squared, and it has coefficient c in front. And now it's time to move to the rest. Other position. So this position corresponds to x1 times x2, but you know what? If you look closely, this position as well corresponds to x1, x2. That is why, so you need to find this term, which is here, It has coefficient 2d. Now this mystery has been resolved. The mystery concerning the fact why they write 2d here instead of d, because this coefficient gets split between these two positions. So we need to find this term x1, x2, divide the coefficient by 2, which will give us d, and split it among this and this guy. They are symmetrical in relation to this diagonal. Very nice idea. So let's move to this position. It corresponds to x1, x3, as well as this position, by the way. So we need to find the term with x1, x3, and see this coefficient. Phi, ff. And finally, these two guys, they both correspond to term x2 times x3, which is this term, and it has coefficient EE. So that's it. Very nice technique to write down your matrix correctly. And now let me give you the rough outline of the algorithm as to how to bring this general form to canonical form. It will be only the rough outline because you're already familiar with this algorithm from our last previous tutorial. So after you write this matrix A, you will need to find lambdas. Lambda 1, lambda 2, lambda 3, which is quite a time-consuming task, but you need to know how to do it, especially in the view of today's test. So I'm going to show you how to find these lambdas once again. The next step will be after this you're ready to find this canonical form. It will look like lambda 1 y1 squared plus lambda 2 y2 squared plus lambda 3 y3 squared is equal to 1. So this will be our canonical form. And looking at this canonical form, you can immediately determine which type of surface is determined by this equation. Okay, but it's not the end to the task, unfortunately, because you are always asked to give this relationship between new coordinates, y's, and old coordinates, which are x's. And that is why you will need to go further. You will need to find eigenvectors now. Find eigenvectors. We denote them f1, f2, f3 because we need to normalize them in the next step. So you definitely started recalling this algorithm for curves, which is the same algorithm. Okay, normalize them. Normalize these vectors. The next step, normalize them. So turn them into E1, E2, E3. Okay, we will do it on a completed example. That is why I don't want to look this outline of the algorithm too messy. That is why I'm not going into details. Finally, after that, you can write the matrix P, model matrix, and after that, finally, you can write down this famous expression y, which is vector y, which has our new coordinates, is equal to P transpose times x. And this will be your answer. And of course, it's recommended to simplify this answer, but we will do it in the concrete example. As you can see, almost nothing new. The algorithm will look the same steps, but it does involve more operations, more calculations, because unfortunately our matrix is 3 by 3 this time, not 2 by 2. And that is why it's quite a long task, unfortunately. But if you got quite a big experience in calculating this, in dealing with matrices 3 by 3, it won't be such a daunting task for you. Okay, let's start. But you know what? Unfortunately, there are only 15 minutes left, or maybe even less. And I wanted to tell you that if you are eager to go to your next tutorial, I would like you to feel free about leaving this session, because my intention is to finish this task, even if I will have to use another like 15 or even 20 minutes, so that you can use my recording, okay? But if you are in a hurry, feel free to leave. I won't get upset about it. I'm determined to finish this task even if I run out of time, because this session don't get interrupted, unfortunately, so I can spend as much time as I like. Okay, so let's start. I choose question 1b from this tutorial. So let's write down this curve, this very big and terrible curve. X1 squared minus 3x2 squared minus 3x3 squared plus 4x1 x2 plus 4x1 x3 plus 12 x2 x3 is equal to 1. So it's quite a big curve, but we know the algorithm. We are armed with our algorithm, so nothing bad about it. Okay, the first step as usual is to write down, let's call it first step, just okay, our matrix A. So 1, 2, 3, 1, 2, 3, 1, 2, 3. These are placeholders. And again, I'm going to write down these associated variables. x1, x2, x3. Maybe I put them here. x1, x2, x3. Okay, let's start with diagonal. So this location corresponds to x1, x1, which is x1 squared. What is the coefficient of 1? Coefficient is 1. Okay. This coefficient x2 by x2, x2 squared minus 3. And this coefficient is minus 3 as well. These positions are more interesting. Let's denote them by orange. So this position corresponds to x1 by x2. So this is this term. So we will get 2 and 2 here. The next position, I'm going to use green, even though I'm running out of ink, but I can use green. Okay, so this position, green position, corresponds to x1 times x3. So this is this term, 2 and 2 here. And finally, I have brown here. So this and these positions corresponds to x3 times x2. We have this term, so it will give us 6, 6. Okay, so we are finished with the matrix. And now comes the most annoying part. Some people just hate this part. We need to find eigenvalues of this matrix. But you know what? This part is especially, this second and the third part will be especially useful for you before today's test. So, you know, I think that, and I have plenty of time until the, okay. So all you need to do, the start is very easy. You need to subtract lambdas from diagonal elements as usual. 2, 2. 2 minus 3 minus lambda, 6, 2, 6 minus 3 minus lambda. And you need to set it up equal to 0. But I'm going to do it at the very end. So now we need to choose the row or the column along which we are going to expand this matrix. I'll choose the first row. Okay, 1 minus lambda times what? We cross out this row and the column, and we are left with matrix 2 by 2. It will be minus 3 minus lambda, 6, 6 minus 3 minus lambda. Okay, then we are moving along this row. The next element is 2, but we need to write minus 2 here. Crossing out this column and this row again, we will get 2, 6, 2 minus 3 minus lambda. And the last term in this row is 2 plus 2. It will be plus 2. 2 times what? Crossing out this row and column, we will get 2 minus 3 minus lambda, 2, 6. So it was relatively easy. The next step will be easy as well, because all you need to do, just calculate this 2 by 2 determinants. Okay, 1 minus lambda. And I prefer to use brackets here because otherwise these things will look too messy already. Okay, so we need to write this guy times this guy is minus 3 minus lambda squared. But you know, looking at this expression, I immediately get annoyed because I hate these minuses inside parentheses. It's better to change them for pluses. It's quite allowed. It's correct, of course, you know. So let's move further on. Minus 36 here. Okay, let's move to the second determinant. Minus 2 brackets again. It will be 2 times minus 3 minus lambda minus 12. Okay, and the last term, the last determinant will be 12, and this will be minus 2 times minus 3 minus lambda. Parentheses and brackets are closing. And now comes the most, you know, terrifying part. You need to do some simplifications, but at the same time, you don't want to do all the multiplications, because otherwise you will end up having terrible cubic equation, and there's nothing worse than to be dealing with cubic equations during exams and tests. You need to be a little bit inventive, resourceful, and so on. So you need to factorize this equation, but right now it looks too terrifying. You know, it's too early to factorize it. But just I suggest we just do some simplifications only about these brackets, So let's try to do this. I hope everything in the field of view. Okay. So maybe this way. Now it looks perfect. Okay, so 1 minus lambda in parentheses gets written, but I think it's better to see, notice that inside these brackets, you are dealing with the very famous formula, a squared minus b squared. And you know how to expand this formula, a minus b times a plus b. I think it's a very good idea. So a is this guy, 3 plus lambda minus 6. So I wrote, instead of a squared minus b squared, I wrote a minus b. And a plus b will be 3 minus 3 plus lambda plus 6. So the first term takes this form. As for this one, I think that we need to do these simplifications inside brackets. Let's do it. So minus 6 minus 12 will give us minus 18. And this times this will give us minus 2 lambda. And let's move to the last bracket, plus 2 times what's inside brackets. 12 plus 6 will give us 18, and this times this will give us plus 2 lambda. And now the most important thing is not to succumb to the temptation to do this multiplication of these three parentheses. It's better to leave them as it is. And besides, we haven't simplified them yet. Lambda minus 3, and this one will be lambda plus 9. And now I think, what do we need to do with these two terms with brackets? I think it's better to do this multiplication, because there's nothing, we can't see anything beautiful here. So plus 36 plus 4 lambda. And this, the last brackets will give us plus 36 again, and plus 4 lambda again. And now, again, let's just rewrite this terrible first term, because I don't think it's a good idea to expand it, to do this multiplication. It's better to leave it as it is. Okay, so let's simplify this part. So 36 plus 36 will be 72, and this guy plus this guy will be 8 lambda. Again, but you know what? We can immediately notice that if we pull out 8, the common factor from here, so we'll get something beautiful. Okay, I'm rewriting the first term again for the 5th time already, but I don't mind it. Plus 8, 9 plus lambda. Look at this. We are very lucky, or maybe we are just very clever. I don't know. Look at this. We have actually two terms here. This is the first term, and this is the second term, and this plus sign is between them. And we do have a common factor. Common factor is lambda plus 9, which is the same as 9 plus lambda. So we are very lucky. Now we can relax. Okay, so we passed the most terrible part of this equation. Okay, so we are pulling out this lambda plus 9, and so all is left of the first term will be this term and this term, and plus 8 from the second term, and it should be put equal to 0. Okay, so it's very nice. Lambda plus 9 is equal to 0. It means that lambda 1 is equal to minus 1. And the second case is this equation. This equation in the brackets is equal to 0 as well. But here I can save your time, actually. So I'm going to write you just the roots of this equation, quadratic equation. So they were 5 and minus 1. So I'm pretty sure that you will have to deal with this cubic equation today during the test. So I think it was very useful to watch this process once again. Okay, so we are finished with lambdas, and you know what? We are ready to do the third step, canonical form. Once you got your lambdas, you can immediately write down canonical form of our surface, which looks like lambda 1 y1 squared plus lambda 2 y2 squared plus lambda 3 y3 squared is equal to 1. In our case, lambda 1 is minus 9, so it's minus 9 y1 squared plus 5 y2 squared, and just minus y3 squared is equal to 1. So this is canonical equation of our surface. And we can immediately determine which type of surface this is. What about signs? We have plus, minus, minus. So it looks like, let's refer to our, it's two-sheet hyperboloid. sorry, it's 2-sheet hyperboloid. So far, nothing bad. But now, unfortunately, we need to find these eigenvectors. And you know it's quite a long process. Because we have 3 different eigenvalues. And it means that we need to solve our equations, system of equations, by Gaussian elimination 3 times in a row. But of course, I'm not going to do everything, I'm just going to show you only the very first eigenvectors. Just to remind you how to do this process. So it was called like step 4, finding vectors f1, f2, and f3. How did we calculate eigenvectors? We always used our favorite equation for this, which is a matrix A minus lambda I subject I times identity matrix times our vector fi current, that is yi, and equal to 0 column, 0 vector. After that, we expanded this notation. This matrix means that subtract lambdas from diagonal elements. But as we did this before, let me remind you, in the very beginning of our task, we did this before. So this was the matrix A minus lambda times identity. So I think it's a good idea just to copy this matrix from here. So I'm copying it here. 1 minus lambda 2, 2, 2 minus 3 minus lambda 6, 2, 6 minus 3 minus lambda, a little bit messy. And our eigenvector has coordinates x1, x2, x3. And 0 vector is just the column 0, 0, 0. So this is the matrix which we are going to deal with. And it's better to put subscript I here just for rigorousness. Okay, and now what we need to do, we need to repeat this process 3 times for every single lambda. So let's start with the first one. Lambda 1 is equal to minus 9, if you remember. What do we need to do? We need to substitute minus 9 instead of lambda y here and start dealing with this matrix. Okay, the first element will be 10. 10 to 2 is the first row. The second row will be minus 3 minus 6, 2, 6, 6. And this will be 2, 6, 6 as well. And what do we need to do with this matrix? This matrix is actually the image of our system of linear equations. The best idea is to solve it by Gaussian elimination. This is just the most reliable method, the quickest one. So let's do it. First of all, you need to look closely at these numbers in each row and decide if it's possible to make them smaller. Yeah, of course, if you divide each row by 2, the numbers will definitely get smaller. This is always a good idea, to make your numbers smaller. That is why let's divide each row by 2. It's much nicer to deal with numbers. The second consideration should be about this top left element. It's always good to have 1 here. And if it's possible to get 1 here, do it. Go for it. So we definitely can see that we can just swap the first and the second row. Let's do it. It always pays off to have 1 here. So 5, 1, 1, 1, 3, 3. So after that, we are ready to apply our Gaussian elimination algorithm. So what do we need to do? Let me run over. The Gaussian algorithm consisted of 2 steps. The first step is to turn these guys to zeros, and the second step was about turning these guys to 0. Because our goal is to get a triangle of zeros here, which will be called row echelon form. So we are ready. If you remember, we always rewrote the first row. And now it's time to start performing the first step, which is about getting rid of these 2 guys. And remember, you're allowed to use the first row only to do this. Okay, so how to get rid of 5? We need to multiply the first row by minus 5 and add the result to the second row. So minus 5 plus 5 will be 0. Here we'll have minus 15 plus 1, minus 14. And here we have minus 14 as well. So instead of 5, we got 0 now. Now let's move to the third row. We have 1 here, and we want to get rid of it, but only using the first row. It means that this row should be multiplied by minus 1 this time. So I write it here just for convenience as usual. So let's start. -1 plus 1 will give us 0. -3 plus 3 will be 0. And this will be 0 as well. Very nice. So we already have this triangle of zeros. We don't need to do this second step. It's been, done without, automatically. Very nice. We are very lucky. Just very lucky. Okay. Again, have a quick look at the rows and decide if it's possible to make numbers smaller. Yeah, it's possible. Look at the second row. Of course, it would be a good idea to divide it by -14. Okay, let's do it. So the second row will be 0, 1, 1, which definitely looks much better. So we are finished. Now we need to find so-called leading elements for each row. So let's look at the first row. It's 1. Leading element is 1. And for the second row, the leading element is 2. Oh, is 1 again in this second row. After that, we look again at this matrix, but this time in terms of columns. We need to find the column or columns without leading elements. Definitely, this is the third column. And this third column corresponds to x3. So x1, x2, x3. It means that x3 is a free variable. X3 is free variable. And we usually denote it like t, like parameter t. And after that, we are ready to get back to the system associated with this matrix. Okay, so the first row corresponds to the first equation, which is x1 plus 3x2 plus 3x3 is equal to 0. And the second equation corresponds, the second row corresponds to equation x2 plus x3. And there is no third equation, it just disappeared as a result of our simplifications. Okay, so now we need to solve this system. But first of all, we need to remember that we already have x3. Now, x3 was denoted as t. And that is why the first step will be just to substitute x3 with t. x3 with t. Okay, x1 plus 3x3 plus 3t here is equal to 0. And the second equation will be x3 plus t here is equal to 0. Then I recommended you to leave so-called basic variables x1, x2 here. Basic are variables which are not free variables, all the rest. So it's better to leave them on the left and move the rest to the right. It's just, very convenient and very efficient. So x1 plus 3x2 is equal to minus 3t. I'm moving this guy to the right, and x2 is equal to minus t. But look at this. We already solved x2. We already have the solution for x2. And it means that, oh my gosh, something happened to my camera. It's so annoying. I don't know. It happens sometimes. Very, very, I don't know. No idea what to do. It's complaining about the internet. I don't know. It's a catastrophe. Of course, I'm going to keep on recording this, but maybe No sound, my goodness. Now we can pull out t, and we will end up having this column 0, -1, 1. And the convention is to omit this t in front. So f1 finally is equal to 0, -1, 1. So this is our first eigenvector. But you know what? Um, I said that really you can see my sheet. Oh my god! And I can see it. For me, it looks like, oh, yeah. Thank you very much that you mentioned it. Oh my gosh, what can I do? And as for me, I have the impression that it's there. I can see it on my screen. Oh my gosh, I don't know what to do. Maybe to switch it off and switch it on again. Maybe it's healthier. Can you see my screen now? Hello, can you see my screen? Oh, such a relief. Thank you. Such a relief. Oh, I don't know why do we get interrupted all the time. Okay, so it's time to finish. So, so this is our first vector corresponding, eigenvector corresponding to lambda. But as I said before, I'm going to save your time. Not time, but it's just not very interesting to go through this process once again, not once again, two more times again. I think it's better to write you the answers. So you already watched this process. That is why there's no point in repeating it so many times. Okay, so let's write down the results. So lambda 1 is equal to -9 gave us this vector f1, which is 0, -1, 1. Lambda 2 was 5, and the vector corresponding to it was f2 equal to 1, 1, 1. Oh, sorry for that mess. And finally, the last lambda, which was -1, gave me vector f3, which is equal to -2, 1, 1. So this is the end of our step 4. Yeah, it was step 4. We did calculate all these eigenvectors. And now we need to move to this next step, which was about normalizing these vectors. I tried to keep everything in the screen. So if I'm not mistaken, this is the 5th step. Normalizing these vectors. Normalizing vectors. Normalize them. Okay, so let me remind you this formula. E1 was equal to F1 divided by length of this vector. So to normalize some vector, we need to divide each coordinate by the length of this vector. Let's apply it to the first vector. So the first vector had coordinates 0, -1, 1. And to calculate the length of the vector, you need to apply this formula. Square root of 0, 1, the first component squared, plus -1 squared, plus 1 squared. I just decided to remind you. So this will give us the square root of 2. So we can place it in front. 0, -1, 1. And it's better to do simplifications actually. 0 divided by -1 divided by square root of 2, and 1 divided by square root of 2. So this is our first normalized eigenvector. Let's write it down. Lambda 1 is equal to -9 will give us the first vector E1, which is, I prefer to rewrite it, -1 divided by square root of 2 and 1 divided by square root of 2. Again, to save your time, and besides it's not very interesting to go through every single vector again, let's write down the results. So for the second vector, for the second eigenvalue 5, we get E2, which is equal to 1 divided by square root of 3 this time. The same second component and the same third component. Okay, sorry, sliding out of view. And finally, the last eigenvalue is -1, and E3 corresponding to it will be our vector F3 divided by its length, which was a square root of 6 this time. -2 divided by square root of 6, 1 divided by square root of 6, and 1 divided by square root of the same value. So these are our final unit eigenvectors. Okay, now we are ready to write down this model matrix. So it will be step 6 probably. I lost count of steps. It's not so important, but nevertheless. Okay, model matrix P. Model matrix P. So let me remind you that model matrix is a matrix whose coordinates are components of these normalized vectors E1, E2, E3. They all have three components here. So let me write it down symbolically. And we are quite ready. We already have these vectors. That is why we need just to substitute them here. So the first column will be the first vector, and it was 0 minus 1 over square root of 2, 1 square root of 2. The second column is the second vector, E2, 1 over square root of 3, the same here, and the same here. And finally, the third column was minus 2 square root of 6, 1 square root of 6, and 1 over square root of 6. So this is our matrix P. And now we are ready for the last step, for the very last step. We need to do what? We need to write down this expression. This y is a new coordinates vector P transposed and times x. So we need to substitute our information into this formula and to do some multiplications, simplifications, and so on. Okay, let's start. What is vector y? Vector y is just a column of our variables, new variables, y1, y2, y2. Then we need to transpose this matrix P, but this is very simple operation. So, for example, transposing means changing the roles of rows and columns in matrix. It means that this guy was the first column now in matrix P, but in transpose it means that it becomes the first row. So let's rewrite these coordinates as a first row. So it will be 0, minus 1 square root of 2 and 1 square root of 2. So this guy became our first row. Again, let's look at the second column. It will become the second row. Okay, let's write it here. 1 over square root of 3, the same, and the same. And finally, the last column was minus 2, 1, 1 over square root of 6. So it will become the third row. Minus 2 over square root, 1 over square root, and 1 over square root. So this was P transpose, matrix P transpose. And now we need to expand on matrix on vector x, which is x1, x2, x3. So this is actually essentially an answer already. But you know, it's always a good idea to do this multiplication. It means that it's better to rewrite it as a system of three equations. It looks much nicer, you know, actually. Okay, so let's do it. It's a very simple matrix multiplication. We need to multiply the first row by this column, and we will get y1. Unfortunately, my handwriting is becoming bigger and bigger. There's not enough space on the screen now, but I'll try to squeeze it in. So now I need to write. So okay, let's switch to the system of equations. So the first equation will be y1. I need to multiply the first row here by this column, and it will give us this times this will be x1. That is why it will be minus 1 over square root of 2 times this guy x2 plus 1 over square root of 2 times x3. So we did get the expression for y1 already. And similarly, we can get the next expression for y2. y2 corresponds to the second row here. Second row times this column will be 1 over square root of 3. You know, it's better to pull it out actually, because it's quite annoying to write these guys. I'll do it this way. So I'm doing multiplication and pulling out this annoying factor as well. And y3 will we get in a similar way. We need to multiply this last row by this column again. And again, it's a good idea to pull out this factor, 1 over square root of 6. So it will be minus 2x1 plus x2 plus x3. So that's it. So it looks like we managed to finish with this task. So that's it. So I hope it was a little bit helpful for you in the light of today's test, especially this process of dealing with cubic equation when you were finding eigenvalues, and also about finding eigenvectors for 3 by 3 matrix. So that's it. Okay, so see you next time. And next time will be in 2 weeks, as far as I can understand, because there will be a holiday in between. Okay, so good luck with your test. You're welcome. Okay, see you next time. Bye bye.